Hi, it's Lee Cosart. In this tutorial, we will look at testing time and frequency in a packet network. It is useful to contrast the measurement of frequency transport with the time transport in a packet network. In the case of frequency transport, one-way measurements are what is important. We can test forward or reverse and evaluate them separately for the characterization of frequency. Asymmetry is irrelevant, doesn't matter. We need a stable frequency, so a primary reference clock is useful. The antenna cable need not be compensated or calibrated for the purposes of measuring frequency. Typical example for packet frequency transport is the 50 part per billion requirement for GSM. For time transport, on the other hand, two-way packet measurements are important. We need to consider both the forward and reverse packet streams and put them together. Asymmetry is absolutely critical. We need both stable time and frequency. We need a primary reference that is able to set a stable time. So we need a PRTC or ePRTC. The GNSS cable needs to be calibrated carefully and compensated. An example of that technology is LTE TDD, which has a 1.5 microsecond requirement. It is useful to look at both testing of physical signals and packet signals and get some feeling for what's going on when we're testing packet networks. I start here with a diagram of a physical signal. Nominally 10 megahertz signal there is shown with timestamps on the rising edges. In the lower part of the slide, you see a series of timestamps, F representing the forward direction, right, R representing the reverse direction. So for example, in the case of the first timestamp, there is a packet timed at point A in the diagram in the lower right. It emerges at a particular time, and then a short time later, that same packet is timed at node B. In a similar fashion, we can consider a physical signal for assessing time performance, in this case a 1 PPS signal, where the rising edges are time-stamped. For the packet case, there is a reference at both nodes A and B with accurate time at both. Again, a packet emerges from node A in the forward direction, is timed there, and then a little bit later at node B. And similarly, a packet would emerge from B for the reverse direction, and then a little bit later is timed at node A. Here is a plot of a physical signal measured using a 1 PPS and a packet signal of the same device shown on the same graph. And as can be seen here, they match very well over this period of approximately 2 days. So this would illustrate that either method can be used to test time. It is useful to contrast the approach we have to physical signals, time analysis, with that for packet analysis. A very important measurement for both is the measurement of phase in the case of physical signals, time interval error in the case of packet signals, packet delay variation. Whereas in tie analysis, we're often looking at frequency, MTI and TDEV. We're focused on statistics quite often for packet analysis, both dynamic and static. The raw phase is important in both cases. It allows us to establish a timeline and see perhaps whether, for example, performance is degraded during times of high traffic. Traditional clock metrics can be applied directly in the case of assessing performance of a grandmaster or a boundary clock, just as they have been applied for a long time to oscillators and synchronization interfaces. For packet networks, some of the modified stability calculations such as min-tdev are useful, as well as we have seen various statistics. In the case of time transport, the time error is the central calculation, and often packet selection is involved, which will be shown in some later slides. Importantly, the time error is a means of assessing link asymmetry. There are two approaches for PDV stability metrics. One involves applying packet selection to the sequence and then applying the standard calculations such as tdev. Another approach involves actually changing the calculation itself. So tdev is changed into a minimum tdev. That's the integrated approach. The packet selection methods usually involve looking at the floor. For example, a minimum can be selected, or some range at the floor, such as the percentile or cluster method, can be applied. The window is an important aspect of packet selection. We can use non-overlapping windows as illustrated in the top plot. We could use what is referred to as skip overlapping windows, where the windows are sliding a few samples, or we can slide the windows sample by sample. This would produce the most number of points overlapping windows. The packet selection itself typically is involving selecting the fastest packets and averaging them together, for example, or picking a threshold and looking for all packets faster than that. Here are some block diagrams summarizing the discussion of the last few slides: the preprocessed packet selection, the integrated packet selection, and another block diagram which incorporates both bandwidth filtering and packet selection. Getting to an example of looking at packet delay variation. The top plot shows the sequence of packet delay. The second plot from the top shows this data organized into a histogram, and there are some statistics on that histogram. You can see, for example, the mean is 96 microseconds in this case. We can then take this histogram and perform a cumulative distribution function and gather some more information about this 15 hours of packet delay variation. Here are some examples of requirements for time, both for equipment and in a network. We can see, for example, time accuracy requirements at the source ranging from 100 nanoseconds down to 30 nanoseconds, and an example of a node in a packet network of a requirement of 1.1 microsecond. The two-way metrics involve packet selection in both the forward and reverse sequences, and then we arrive at such calculations as the packet selected two-way time error shown in the fourth equation. It is useful to contrast the ideal for the case of either of the one-way sequences. The ideal there is to choose the lucky packets, the fastest packets. In the case of two-way time error, the ideal case is 0, so that would indicate no asymmetry. To dig down a little bit and further illustrate how the packet selection works followed by the combination of the forward and reverse streams. There's some raw data depicted at the top of this plot, a forward packet delay sequence on the left, a reverse packet delay sequence on the right. These can be combined to arrive at a two-way data set. And then finally, at the middle of the slide at the bottom, there is a search performed on the forward and packet sequences, which then result in the two pairs that you see there, 1.23, 1.09, and 1.4, 1.05. These are the packet selected forward and the packet selected reverse sequences. And then it's a matter of applying these packet selected sequences to the minimum two-way time error, subtract the two point by point, and then we arrive at a minimum two-way time error, first of minus 0.07 microseconds, and for the second sample, minus 0.18 microseconds. A couple of real examples where data has been gathered in the field. A two-way time error, the raw data is shown on the left. In that case, there is a 22.2 millisecond peak to peak, quite a large value when precision time is the goal. And the mean in this case is 378 microseconds. When packet selection is performed on the forward and reverse, and we actually look at the packet selected two-way time error, these numbers are reduced to useful values for transporting time. The peak to peak is now 663 nanoseconds, and the mean in this case is less than 1 microsecond, 456 nanoseconds. In this example, network asymmetry is illustrated. The top plot shows a measurement of the network itself, a packet network. In this case, on the x-axis is a range of round trip values, and on the y-axis, the time error with packet selection. So for the fastest packets, the lucky packets, the value turns out to be 2 microseconds for this network. The lower plot shows a measurement of a IEEE 1588 client subjected to this network asymmetry. And what can be seen there is that after a period of 30 minutes or so, the client settles in on a value of 2 microsecond, matching what would be predicted from the network measurement. Further example of network asymmetry. In this case, a test was made over 150 kilometers of fiber. This is PTP over OTN transport. The forward and reverse sequences are shown in the small plot to the upper right. And in that case, there is a difference between the two. The reverse comes in at 2.066 milliseconds, the forward at 2.028 milliseconds. So there is a 38.2 microsecond difference between the two, and this translates to 19.1 microsecond asymmetry exhibited in this network. Very stable over this 41-day period. To summarize, PDV frequency measurements only require a stable reference. PDV time measurements require a common timescale reference at both ends of the network being studied. GNSS is a way to do that. For frequency transport, asymmetry doesn't matter, but it matters a lot for time transport. As we have seen, it is very prevalent in many networks, and it certainly has a direct bearing on the ability to transport time. The metric two-way time error is a direct means of looking at asymmetry. There are two ways to assess time transport, either the 1 PPS physical signal or looking at the packet signal at a node. Packet metrics for time transport must use both the forward and reverse streams together. Packet metrics for time transport can make use of much of the methodology for packet frequency transport metrics. Thank you.